So when we're talking about linear regression, we've got several different measures that we use that are all important and have different applications. We've talked about the SSE, the sum of squared errors, and we talked about the average error, which is related to the SSE. And there's a third measure that we use called the correlation coefficient. And what the correlation coefficient is it's a measure of the level of correlation between the two variables involved. So when I say two variables, I mean, you have if it's time and population, that's a very common one. So time would be one variable and population would be the other. And what does it mean to be correlated? Well, just as in common parlance, correlation means as one thing changes, the other thing changes. Okay. And so we can have linear correlation, meaning as one thing changes, the other variable changes linearly. We have other types of correlation, which we'll get into later. And you can have different levels of correlation. So a truly linear function is perfectly linearly correlated. And as you kind of move these points out of a linear distribution, the correlation weakens and weakens. Okay, so that's just a rough idea. The letter that we use to symbolize correlation, the correlation coefficient, is R. That's a little bit of an unfortunate choice because we use R for lots of other things, but for the moment, R will be correlation coefficient. Now, where is it? Well, right here is its location in the calculator. So you go to var statistics equation. Let me show you. So assuming that we have a function entered with data and so forth, we would go to vars. Number 5 is statistics, and then you scroll over to EQ. And notice under EQ, you've got a bunch of letters here. The one that we're particularly interested in right now is number 7, that's R. But I'll just go ahead and point out that if for whatever reason, if you want just the A value, which is the slope, or you want the B value, which is the intercept, you can call those up specifically just by selecting number 2 or number 3. For a linear equation, we don't have these other letters, so there is no C, D, or E. Well, there is, but it's 0, so. But anyway, that's how you get the correlation coefficient. So we would just scroll down to that R value and hit enter, and then it would bring it up. So the nice thing about the correlation coefficient is it's not something that you actually have to compute. You just have to click a few buttons and go to it on the calculator. Okay, so what do we do with it? What does it mean? I'm going to be flipping back and forth between these two slides here, one that says selected critical values, and I know I haven't defined critical values yet, but I will in just a moment. But first, let's talk about how we kind of interpret the correlation coefficient. So let's suppose that we have a set of data that has n points in it. So think n can be whatever your favorite small number is. In the example that we're showing here, we've let n be 10. So we have 10 data points. And let's assume that our correlation coefficient, we found it to be some value r. Now, that at r value, whatever it is supposedly gives you a numeric measure of how strongly correlated the two variables are. But we kind of need some way to interpret that and to decide, like, what does that actually mean? Because if it's sort of on a sliding scale, at what point do we actually decide that we're far enough on the scale to say that they're correlated or they're not correlated? Well, it's sort of it's sort of it's not necessarily that we have a hard line. It's just basically that we have to decide how confident we want to be in correlation. And if you've taken statistics, you've probably done some things with confidence intervals, and so this may seem somewhat familiar to you, but a kind of a basic thing in statistical reasoning is not that you have a firm yes or no answer, but that you set a level of confidence and then you ahead of time, and then you see if your data measures up to that level of confidence. Okay, so the higher you set your level of confidence, the more the closer you're getting to just being absolutely sure, right? So what we are going to do is we are going to set our confidence level to be 95%. In statistics, you play around with this and you work with different confidence levels, but for this class, we're fixing it at 95%, okay? And what we're going to look for is that the correlation coefficient meets or exceeds another number which is related to this 95% confidence. And that other number is this thing called the critical value, which is on this slide. Okay. This is again harkens back to statistics, and if you've taken statistics, you probably worked with critical values. If you haven't, that's okay. We're not going to be going very deeply into this. We're basically just going to be using this chart. So this is not, obviously, we're not going to expect you to memorize this chart. You can use this for reference if you print it out and so forth. But anyway, so what's the idea? So in our example, we have 10 data points, and notice here that we've got a column that says n, and in n you've got different numbers of data points. And notice also that it starts at 3. The reason for that is that if you have 2 data points, then 2 points will always have a line exactly passing through them. So they'll be perfectly correlated. So we start with 3 and then we go up from there, okay? And associated with each n value, there's a critical value. This is not a correlation coefficient. These are not correlation coefficients. These are critical values. And you can think of them as lines in the sand that the correlation coefficient needs to surpass. Okay. So in our case, we're down here with n equal 10, and the associated critical value is 0.632. So here's the way we're going to use this. There's actually we can actually think about this positively and negatively. Let's talk about it positively first. So here's R sub 10, which is 0.632. And this is just, think about this as a normal number line, so this is going positive direction, negative direction. And what we're going to see is, where does R, the correlation coefficient, fall? Is it here, or is it here? If it falls over here, then it exceeds this value. And so we would say 95% confident that it is linearly correlated. Let me see if I have room to write that. Correlation. Okay. Whereas if we fall over here, so that R is smaller than 0.632, then the way to interpret this is that we cannot be 95% confident in correlation. Okay. So on this other slide, we go into this in a bit more depth. Now notice that I said that we could think about this both positively and negatively. I've got both of these on this picture. The other important thing to think about here which I don't think I've mentioned this yet, but the correlation coefficient is always going to be a number. So R is always going to be a number between between -1 and +1, between -1 and +1. So R is less than or equal to 1, but greater than or equal to -1. If we're over in the realm of negative numbers, then we're talking about negative correlation, and these things have specific pictorial understandings, which we'll look at in just a moment. But so negative correlations over here, this is perfectly positively correlated. But when we're looking at interpreting the line in the sand argument, sometimes what we do, because if you get a negative correlation coefficient, you basically just flip the picture around. So in this previous slide, I was just talking about positive correlation, and I said, well, if you're over here, then you are 95% confident. If you're over here, then you're not. Whereas for a negative correlation coefficient, if you're over here, which is further to the left, but also bigger in magnitude, in quantity than the critical value, then you are 95% confident in negative correlation. Whereas if you're over here, then you cannot be 95% positive. I'm sorry, 95% confident in negative correlation. One way to deal with that is just to take the absolute value of your correlation coefficient, and then you don't have to think about whether it's positive or negative when you're making that decision. Okay. But to talk some more about this picture, notice that this is a scale that goes from -1 to +1. As we approach 0, correlation weakens. So R close to 0 is no correlation. When we go above 0, we get into the realm of positive correlation, and when we go below 0, we're in negative correlation. Okay. Now, I want to skip to visualizing this so that you can think about what these types of correlation actually look like. So here's, on this slide, you're looking at 3 distributions that show different types of correlation. So this is positively correlated, positive in the sense that it's increasing. That's what we mean, or it has an increasing trend. This is negatively correlated, and both of these are pretty strongly correlated, because that if you kind of squint your eyes and blur your vision, you can see that this is definitely got both have linear behavior. But negative correlation it kind of corresponds to a decreasing function. And as we approach 0 from either side, you just get this scattershot distribution that seems to have no correlation whatsoever. Okay, so that's what we mean by positive, negative, and no correlation. All right, let's look at an example. Back to this population model. And we had this in the calculator earlier. I'm not sure if I might have already deleted this. If so, I'll pause the video and re-enter the function. Yeah, I have. Okay, well, let me pause the video and I'll re-enter the function, and we'll get the correlation coefficient and run this test.